this computer. Okay, so the way this is going to work is going to work pretty much the way our lectures did in class, which is that I'm going to do a bit of an introduction into these problems, and then I'm also going to, and then I'm going to, rather than going around the room like I normally do, I'll split us up into breakout rooms. Okay. And then we'll go through the breakout room. I'll go through the breakout rooms and help people in the order of the breakout rooms. So you can self-select, you know, if you need to leave early, fine. But I do think I do, because, you know, I don't take attendance, but I do suggest you stay so that I can help you out with these so you don't fall behind. If you need help, sure. If you need a demo, great. For some questions with demoing, if you've got it on paper, that might be a bit difficult, but hey. So let's go ahead and talk about the Josephus problem, okay? So Flavius Josephus, okay? The Josephus problem is named after this guy. He's actually fairly of minor historical importance, or possibly a lot of historical importance, depending on your field of study. I don't think any of us, for him, he's majorly important, but he's fairly. He was born Yosef ben Matityahu. So, and it says here he was a Roman Jewish historian. So what he was is that he was a priest. He was a war leader. So, and what happened is that there was a Jewish rebellion against the Romans in the early 100s, right? Like, or mid 100s, I should say, not mid 100s, mid zeros. Okay, right? 0 CE, you know. So basically there's a revolt against the Romans. And this went exactly basically as all the other revolts against Romans go, which is extremely poorly. The Romans are very good at war, very good at crushing dissent. And that's just very good the way they were very good at maintaining control of their empire. Okay. So, what happened is that he led his troops, and as the story goes, he and his band of like 40-ish people were basically, you know, kind of stuffed into a cave. You know, they basically were trapped in a cave, and the Romans basically said, if you surrender, we will enslave you, rather than kill you. Which, you know, slavery in the Roman times didn't necessarily have to be for all your life. So, but the Jews there decided, you know what, we'd rather die than be slaves, and so they drew lots. We'll get into that process. Actually, I'll get into the process now, and that is where we get the Josephus problem for. Rather than, you know, each of them deciding to kill themselves, they decided to draw lots to decide how to kill each other. Yeah, very dark here right now. So Josephus problem. Here we go. Influence, Josephus problem. And the way that it traditionally is kind of thought out is that the soldiers stood in a circle, and then they counted off every other person. Here it's every other person, so every third person. And what they would do is that they would draw lots, and 1, 2, and then this person would be killed, and then 3, and then 4, 5, and then kill this person. 7, 8, remove this person. We'll go to remove now. 10, 11, remove. And it'd go on and keep spiraling in. As you can see, people get, so with 41 soldiers and killing every third person, eventually you get to person 31 and person 16 remaining. And anyway, the idea here was that basically that most of the Jews there killed themselves, but Josephus was left as one of the last 2 people, and I guess they kind of looked at each other and went, well, that was a terrible idea. Let's surrender to the Romans, and they did. So he became a slave to Vespasian, and basically said, hey, you're going to be awesome because our prophecies say you're the Messiah, totally, and you're really good at war, so I bet you're going to be emperor too. And Vespasian did become emperor, and as a result, Josephus got his freedom, which he then used to stay in that family and write a bunch of historical stuff. And this is why he's of importance besides this weird this really weird and morbid mathematical problem. He's, if you notice when he's alive from, that's 37 to 100. So he wrote the Jewish War, about that kind of thing. But that entire time period is early Christianity. We're talking really early. And this gives us historical accounts of that time, of Judaism during that time, and really early Christianity. Firsthand accounts there, you know? So this is like a lot of really nifty stuff for, a lot of juicy stuff if you're into that kind of personal area of history. So, just a general kind of interesting thing that we get a problem from him. Now, the entire point of this being a linked list problem, okay, in other words, where if you have a game and you're standing, and we can define this as basically kind of an eeny, meeny, miny, mo problem. Given a number of people in a circle, and we're moving every kth person from the circle, where should you stand to be the last person remaining? That's what the Josephus problem is asking. And we have actually, of course, since it's a math problem, we have a case. We have a formula for it. And this looks awful, doesn't it? Right? Just take a moment to marvel in this beautiful equation that somebody figured out that says, hey, given the n people and kth people and every kth person, where do you stand? Did somebody bother writing that? And that's kind of that's a lot. That's intimidating to me. So instead, what we're going to do is, rather than just try to solve it, is that we can make a circular linked list to simulate this problem. A circular linked list to simulate this problem, and that's what we do here. So for this problem, let's see. Let me switch windows for a second. So again, for this problem, where you want to start is, and this is true for the solitaire encryption, where you want to start is doing this. Add E item. This add size item, return true. We just simply flip that to true. So the add method's already done. We don't need to actually change the circular linked list constructor, because guess what? Even though it says implement the constructor, it's done, because you want to set, with the constructor, you want to set head to null, tail to null, and size to 0. But if you don't give them a value, Java automatically has to fill in a value for them. So it fills in basically 0 values for everything. For objects, that's null. For ints, that's 0. And for Boolean, I believe that's false. So you want to implement this for add. This part of the add is done. This is half of where the meat is in the program. So this is about half the work. And I'd say about another 40% of the work takes place over here. Okay? Which is this over here, the remove method. Obviously, you want to get the add method working and then test it down here in main. Now, and then this toString automatically works. It will crash if it doesn't work correct, if your code doesn't work correctly. So that's a way for you to test your code. Finally, we've got this thing over here called iterator. Okay. And it works like this. Okay. This is probably the most important part of my entire spiel. Okay. Which is that we've got I'll create a circular linked list of integers, right? It doesn't matter that nothing's implemented. I can still call those methods. That's the beauty of doing object-oriented programming like this and having your code always compile, is that you can call the code that you know is not going to work, so that you already have a test written. Okay. List is equal to new linked. So not circular. No, cannot undo an exception. That's very interesting. I've never heard of that one. Circular linked list. Okay, there we go. We've made a new circular linked list. And what we'll want to do is that we will want to, let's say, add 5 things to that list. Let's go with the numbers 1 to 5. Okay, it's not going to add them because I haven't implemented that yet, but that's fine. I'm not going to be running it. List.add. My entire point is to show you how the iterator works. Okay, which is this mysterious thing. So list.add I. Okay, now if you're doing solitaire encryption, this part doesn't pertain to you at all. This part is uninteresting if you're doing solitaire. So this is only for the Josephus. So now, once we've added everything, we can do list.iterator to get the iterator. Now, normally you never call the iterator like this, but in this case, you kind of want to manually iterate over it. This is kind of what gets called this is kind of what gets used when you do a for each loop. So I'm just going to call it iterator iter. And we want to give it a type. It wants a generic type. Since we're iterating over integers stored in a list, it's a integer. And then what we can do is that we can do iter. So we created this iterator, which is a private class that is stored in here. And it has 3 methods that I describe here, as required by iterator. It has next, which says, is there, I'm iterating through this thing one at a time. Is there a next thing to iterate to? In a circular linked list, unless it's empty, that's always going to be true. Dot public E next, which automatically goes to the next item. It automatically will also handle wrapping around the circular linked list. I've already implemented that for you, so you don't have to worry about, oh, if I get to the end of the circular linked list, do I have to shift indexes? The entire point of the iterator is that you don't have to worry about indexes in this entire main method. Okay, so don't worry about the indexes. I've already done that for you here with the iterator when you're iterating through it. And then the other thing is remove. Okay, remove, as I cite over here, removes the last node visited by the next call. For example, if we just created an iterator, the following calls would remove the item at index 1, which is the second item or second person in our ring. Dot next would get us to index 0. Dot next gets us to index 1. Dot remove, that removes the thing at index 1. Everything automatically shifts. The way remove works, sorry, it's not a freebie for you. It calls your remove method to do that. And it calls your remove method on a specific index. So you create the iterator over here like this, and you create a loop. And you've got these methods here that you can use. Specifically the ones you could call has next, but you're not going to want to. Instead, you want to call next and remove. Those are your things. Okay. That's the last 10%. Okay. For the solitaire encryption, this comes from a really cool book called Cryptonomicon by Neal Stephenson. Neal Stephenson is a pretty amazing author. He has one glaring weakness, especially in his earlier works, which is that he doesn't know how to stop writing. And most of the time, for a lot of his books, it feels like his editors snuck in at the middle of the night and stole his manuscript and just decided to publish what he had because he just wouldn't stop writing. They are real doorbusters. The most accessible of his work is about Reamde, is called Reamde, R-E-A-M-D-E, which is a misspelling of readme. It's about gold mining in China. It's about the Russian mafia. It's about international terrorism, flight plans, and how to alter them. It's a really good book. It's a really wild ride. And it reads like a nice, very good action novel with bits and pieces interspersed into it. Where you just get a kind of info dump. It's a really fun thing. Anyway, in one of his books, called Cryptonomicon, which is about the history of cryptography as well as kind of the 1990s cryptography, 2 people needed to communicate secretly with each other using an encryption algorithm. Cryptography is the art of making codes. Cryptanalysis is the art of breaking codes. So he wrote to Schneerson, what is Bruce Schneerson? I forget the name. Give me a second. Bruce Schneerson. Oh, Schneier. It's just Schneier. Bruce Schneier, who's a famous American cryptographer. and said, hey, I'd like an algorithm for my book. It involves a deck of cards. Can you help me figure out an encryption algorithm that's based off of the deck of cards? And he said, sure, I'd be happy to do that. And that's where you got this algorithm from. With regards to getting so you can find more about that in the write-up. With regards to my hints, because again, it's more work. Let's see, the entire screen, share screen, just this one. With regards to the to this, okay. So first off, I've already done one of the things for you for encrypting characters. Given a letter and a key, which is basically how much I want to encrypt this thing by, or what the offset is for this character, I'm going to go ahead and encrypt this character. And same for decryption. Okay, and it does some weird things that you should maybe just know that you may, or you may have known, but you completely forgot about. For instance, I take in a character over here, and I subtract from it another character, and the end result is an integer. What? Why? Okay, well, remember, characters are just kind of ASCII, or now UTF-8, meaning they're just numbers. So I can do subtraction and addition with characters. Here I am subtracting the value 97, lowercase a, from whatever letter. Why am I doing this? The reason I'm doing that is because trying to figure out encryption is really hard when I have to like start at 97. I'd much rather each number be assigned a value from 0 to 25. So that's what I do. This gets everything in between the 0 to 25 range. And the modulo makes sure I keeps it there. And then I just add the A back in to get what the real letter is. And the reverse happens over here. Okay. Now I've already kind of created the method stubs for you over here. But as far as where you should start, you might be thinking, okay, I go in order, get key, implement 1, 2, 3, 4. Don't do that. Start on circular linked list step 3, which takes in a deck and performs a triple cut on it. Now, how do you perform the triple cut on that? What I would do is, my hint here is I would take this and I would create 3 new decks: top, middle, bottom, and move all the decks over and move all the cards in here into one of these 3. Depending on what on the specific card. That's my hint there. If you need more than that, I'll be happy to sit down and work on that with you, but that's my hint for that one. All right, any questions before I split you up into breakout rooms? And again, hopefully you've all been able to hear me. So, if there's no other questions, no DMs or whatnot, I will go ahead and let's go and click on breakout rooms. We have 24 people currently in here, including me. So let's go ahead and I'll make 8 breakout rooms. That's going to be 2 to 3 people. I'm going to click let participants choose your own room. I will go from room 1, 2, 3, 4, in order. I'm also going to enable screen sharing so that you can share your screen with your fellow students. Okay. So stop recording.